It's now time to talk about binomial series. So this is the last major topic in our entire 2 chapters worth discussion of series. So this is sort of not really the culmination of what we're doing. It's just another type of power series. Working with power series is really the culmination of what we've been working towards. But we do want to find out what a binomial series is. It is a Taylor series. In fact, it's specifically a Maclaurin series centered generally at 0. And it's based on a binomial, 1 plus x raised to some power p. Now, binomial type patterns show up in all kinds of real world applications and everything from biology to oil exploration to traffic on the internet to all kinds of places. So we've got this 1 plus x raised to a power pattern showing up in lots of places. So we'd like to have a Taylor series expansion for it. So the first thing we want to do is we want to define what is a binomial series. It is, in fact, a binomial series is a Taylor series, and specifically it's a Maclaurin series. So it's centered at 0. And it's for the function 1 plus x raised to a power p for any real number p. And this is known as the binomial series. Now, if p is a whole number, of course, it's just going to terminate and it's going to become a finite polynomial, which you can see right here in these expansions that we've got. So in the simplest case, that's the simplest case, p is a whole number, 0, 1, 2, 3, one of the counting numbers plus 0. 1 plus x to the 0th power is just going to give you the number 1, which is, anything to the 0th power other than 0 is 1. So that's simple. And 1 plus x to the first power is just 1 plus x, or 1 plus 1x. 1 plus x squared, well, you can use FOIL to multiply it out, or the distributive property, and you get 1 plus 2x plus 1x squared. 1 plus x to the third is 1 plus 3x squared plus 1x cubed. And then 1 plus x to the fourth is 1 plus 4x plus 6x squared plus 4x cubed plus 1x to the fourth. And what we're going to see is that there's a pattern developing here. And we can see right here on this one, looks like I forgot to put my 1 in there, so I should make note that I should come back and add that into the notes. Do you see that these are all starting with a coefficient of 1 and they're all ending with a coefficient of 1? So what we're actually developing here is what's known as Pascal's triangle, or Yang-Hui's triangle. Pascal used this in the 1600s, late 1600s. It was called Pascal's triangle by someone in about 1708. But Yang-Hui was a Chinese mathematician, and he was working with this in the 11th century, so in the 1000s. So the expressions on the right side, this is known as the binomial expansion, where you've multiplied it out, and the constants, the coefficients, are known as the binomial coefficients. And as we're going to see, they relate to Pascal's triangle. Now, when we're looking at these, for any non-negative integer p, in other words, for a whole number, we can express those coefficients by computing this relationship right here. This is called p choose k. Your book is using r choose n, which is actually backwards, which is why I'm sticking with p and k. Most books use n choose r, so I didn't want to use what the book was using. This is p factorial over k factorial, p minus k quantity factorial. So when we're looking at these, this will actually give us, when we multiply all that out, it will actually generate these numbers, the 1 here, the 1 and the 1, the 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, etc. So this formula will generate these binomial coefficients, provided that the power on the binomial is a whole number, so 0 or a counting number. Now, if it's not a whole number, then we'll have to come up with another formula in order to find those coefficients, right? Now, there's another way of thinking about this, which gets into probability and statistics. It's called the number of combinations of things taken a certain number at a time. So let's pretend for a minute that we want to pick r different objects from a set of n objects. So for example, let's say you've got a hockey team with 15 players on it. So n equals 15. All right, so we've got n equal 15 down here. And you want to choose 5 players to go on the ice. So you're choosing from a set of 15 players, you're choosing 5. All right, so we would call this n choose r, right? So that's another way of expressing this up here, n choose r, which is n factorial over r factorial n minus r factorial. So this gets into the number of combinations. How many different ways could you choose these 5 players in no particular order from the 15? Well, I would compute that, and let's see what we get. So this would come out to be 15 factorial over 5 factorial times 15 minus 5 factorial. Well, that's 10 factorial. So this is going to give me 15 times 14 times 13 times 12 times 11 times 10 factorial, running out of room, over 5 times 4 times 3 times 2 times 1 times 10 factorial. So the 10 factorials cancel. And let's see, what else have I got? Well, I've got 5 times 3 in the denominator, which will cancel at 15 in the numerator. So the 5 and 3 cancel the 15. And then I've got a 4, and 4 can go into 12 and leave a 3 behind, and 2 can go into 14 and leave a 7 behind. And now you need to grab a calculator, and I'm hunting for my calculator on my desk, which is kind of a wreck. So what have we got now that we're looking at? So we've got in the numerator, we've got 7 times 13 times 3 times 11 and divided by 1. So that gives me, whoa, this is pretty amazing. So this value for 15 choose 5 turns out to be 3,003 ways. There are 3,003 ways that you can choose 5 players at random from this set of 15, which is pretty phenomenal if you think about it. All right, so this is what we call 15 choose 5. And there are other ways of writing this. Sometimes you'll see it written with an uppercase C. The number in the set comes first, and then the subset you want to choose from that comes second. So it can be written as 15 choose 5. And sometimes it's also written in more notational form as 15 choose 5. Now, I prefer personally this form right here because it kind of reads in the order that I mean it. Out of 15, I choose 5, right? So there are lots of different ways of doing that. And this will, in fact, generate the coefficients that we see up here, right? Now, I am not going to use the n and the r very often because the book, instead of doing n choose r, which is the way most books do it, they did r choose n, which is backwards. So I'm going to stick with p and k most of the time. Now, how do you find these combinations and permutations on your calculator? So they are on calculators. If you have a graphing calculator like this, then you want to hit the math key and you'll get 4 options across the top. There'll be math, number, combinatorics, and probability. All right, or complex, rather, not combinatorics, complex and probability. And then what we want to choose is probability because combinations is a part of probability and statistics. So use the right cursor to move it over PRB for probability and scroll down to option 3 or hit the number 3. And that will give you combinations. Permutations, where the order matters, is choice number 2, and combinations is choice number 3. And permutations are written in a similar fashion to combinations, but with an uppercase P instead of an uppercase C. Now, in order to use the combinations on the graphing calculator, what you want to do is you want to first enter the number for n on the screen. So starting from the main screen, enter 15, then hit the math key, right cursor over to PRB for probability, scroll down to option 3 or just hit the number 3 and hit enter. Then you want to enter the number for the subset that you want to choose, which is 5. and then hit enter. All right, and you should come up with 3003. I also recommend the sharp right view for a scientific calculator. And the scientific calculator, this particular one, you tend to find the combinations and permutations on keys 5 and 6. They may be one order or the other, but they tend to be above the number 5 or the number 6. And my particular one, permutations are above the number 6 and combinations are above number 5. So to use it, you're going to hit the second function key, and that will give you the combinations. So what you want to do is you want to basically enter the number for the total number in the set, the 15, then the second function, and then the number 5 key. And then you want to hit the number for the subset you want to pull from that set, and then hit enter. And you should again come up with 3003. Right? Now, keep in mind when you're using calculators that calculators, factorials, grow extremely fast. They grow much faster, much faster than exponentials do. And we know that exponentials grow incredibly fast. So this makes factorials like exponentials on steroids. They're just like crazy fast. So it very quickly, your calculator is going to go, what, can't do it. All right. So for example, on the one we just did before, it might have thrown up its hands and gone 15 factorial, not doing it, or you never know. So when that happens, you'll get an error message. It doesn't mean it doesn't exist. It just means that the number's too large for the calculator to handle. So for those type problems, just do them by hand. Let's now take a look at Pascal's triangle, also known as Yankee's triangle. And this is going to develop those binomial coefficients that you see. It's always going to start with a 1, and it's always going to end with a 1, all right? As we saw when we expanded the binomials to whole number powers, the coefficients always started with a 1 and ended with a 1. And there is a pattern to it. So what we do is we create a pyramid type shape that you can see right here. And we're going to start with 1 because anything to the 0th power is 1 other than 0. And then the next row, we have a 1 on the left and a 1 on the right on either side of this one, because we always start with a 1 and we end with a 1. And then for the next row, we're going to start with a 1. And then to get the 2, we add the 2 numbers above it on either side. So 1 plus 1 is 2, and then we end with a 1. Then we start with a 1, we end with a 1. To get this number, I take the 1 plus 2, which gives me 3, and then 2 plus 1 gives me 3. So I get 1, 3, 3, 1. Remember, those were exactly the coefficients that we got when we took 1 plus x and cubed it. So we start counting the row with row 0 because this corresponds to the 0th power. And then row 1 corresponds to 1 plus x to the 1st power. Row 2 then corresponds to 1 plus x quantity squared, which gives us the coefficients 1, 2, 1, and so on. When we look at the individual elements or terms inside the triangle, just as we do with rows, we start counting with the 0th element. So this is the 0th element of row 5, first element of row 5, second element of row 5, and so on. And in fact, these correspond to those combinations that we talked about earlier that you can find with p factorial over k factorial, p minus k factorial. So this one right here is in row 5. So this one right here is going to correspond to 5, choose 0. The 0th position gives the subset number, and the row number gives the total number in the set. So this second one is 5, choose 1. In other words, from a set of 5 things, how many different ways can I choose one of them? 5 ways. I know that sounds crazy, but that's true. There are 5 ways to choose one thing from a set of 5. You choose one of the 5. What about this next one? Well, this next one would be 5, choose 2. In other words, how many different ways from a set of 5 things can I pick 2 at a time? 10 ways. All right. And then the next one is going to be 5, choose 3. And then we have 5, choose 4. And then we have 5, choose 5. And this makes sense now. How many ways from a set of 5 can you choose all 5? Only one way. There's only one way that can happen. So you can see why we always end with a 1. So how can you choose none of them? Only one way. How can you choose all of them? Only one way. That's why we start with a 1 and end with a 1. All right. Here is what it looks like when you expand the binomial to a whole number power and you write it right next to Pascal's triangle. And of course, this is the exponent, which also corresponds to the row number. Remember, we start with row 0, we start with element 0. So this is technically 0, choose 0. How many ways can you choose 0 things from a set of 0 things? One way. And so you can see that these coefficients that you're seeing here in Pascal's triangle are the coefficients when you multiply out that binomial on the right? So you may have never realized that it can be done that way. And we did this previously using the P choose K notation, but that can also be written like this in this sort of matrix format right here. So for example, if I'm looking at this one right here, this 4 choose 3 is the same thing as 4 choose 3. From a set of 4 things, how many different ways can I choose 3 things? So I need row 4, which is actually the 5th row because we start counting at 0. And for 3 things, again, we start at 0. So 0, 1, 2, 3. So there are 4 ways that I can choose 3 things from a set of 4 things. So this is sort of the relationship between the binomial expansion and Pascal's triangle, right? And I do have a very large one that I include in my notes. I can't imagine that you're ever going to need more than up to power 10. Even that's pretty rare. It might not be uncommon to go up through maybe row 6 or row 7. Again, notice that the second value in the row actually gives the row number. This one doesn't have a number, so it's row 0. This is row 1, row 2, row 3, row 4, and so on. All right, so that's another thing that helps. And notice that they're symmetric going across. So it builds up a pattern and then it goes down the same pattern. And that is constant in Pascal's triangle or Yang-Hui's triangle. So now what we want to talk about is we're going to talk about the binomial series. So we've talked about how we can use Pascal's triangle to find the coefficients in a binomial expansion where the power is a whole number. But what if it's not a whole number? If it's a whole number, we can use this formula n factorial, r factorial, n minus r factorial, or p factorial, k factorial, p minus k factorial, where the upper is the total number in the set and the lower is the subset you want to pull from it. But if it's a real number, then we can't use this formula because it doesn't make sense to talk about factorials when you have a number like -3 or a number like 1/2. I mean, what does that even mean? What's a -3 factorial? Well, it doesn't have meaning, and neither does 1/2 factorial. So we have to come up with a new way of developing those coefficients whenever p is a real number that's not a whole number. So it could be a negative integer, it could be some kind of rational number, it could even be irrational. When that happens, 1 plus x to that power will not be able to be written as a finite polynomial. The only ones that become finite polynomials are when p is a whole number, the ones that we saw previously. But when it is something other than a whole number, it becomes an infinite polynomial. We can find a power series for it centered at 0. So when we're doing that, we can show that the coefficients of the binomial series will actually be given by this down here. Now you should recognize this front part right here. This is basically how you expand a Taylor or Maclaurin series, specifically a Maclaurin, because you find the kth derivative, you evaluate it at 0. Remember Maclaurin series, a is 0, and then you divide by k factorial. Now, why do you get this pattern on top divided by k factorial? the k factorial is coming from the coefficient pattern. The numerator is coming from taking the derivative of this repeatedly. So we pull the p to the front, and then this becomes p minus 1. And then the next time we do the derivative, we get p times p minus 1, and then this becomes p minus 2. And then we pull that to the front, so we get p times p minus 1 times p minus 2. And we do this until we reach the kth derivative. And the last thing we pulled to the front was p minus k plus 1, right? And so this actually comes from the development process for a Maclaurin polynomial. So we can see where it's coming from. And this will give us the coefficients. So writing it in this format is the same thing as we've been doing, but it also represents now this p choose k that we have right here, where p is not necessarily a whole number. All right. So when we're looking at this particular expansion, we can write this as a power series. Remember, the power series has x raised to a power on it. So here you see the coefficient of it right here, which was the kth derivative of the function divided by, at the center, divided by k factorial. And ours is centered at 0. And we can also write it with this p choose k notation, x to the k. All right, so this is what we have. And when we're looking at it in this format right here, one of the things that you're going to see right here is that we've got the 1 factorial, 2 factorial, 3 factorial, 4 factorial, and those are matching the power that we have on the variable x. So when we have 2 factorial in the denominator, we have x squared. We have 3 factorial, we have x cubed. But there's also another pattern that has developed here that you may or may not see, and that is that the number of factors that you have in the numerator matches that power and that factorial. So here I only have 1 factor in the numerator, which is p, and I have 1 factorial and the first power. Then I have 2 factors in the numerator, p times p minus 1. That's 2 factors, and that's 2 factorial and x squared. And I have 3 factors over 3 factorial x cubed, 4 factors over 4 factorial x to the 4th. That is a pattern that will continue indefinitely. Now, when we're looking at this, if we want to know where it converges, we can use the ratio test for absolute convergence to find the interval of convergence. And then we have to test the endpoints separately, just as we saw previously when we were looking for intervals of convergence. So we're expanding this p choose k now. This was the formula that we used whenever the powers were whole numbers. And this is the formula that we're using over here when they're not necessarily whole numbers. And in fact, they are equivalent if they're whole numbers. So you can expand p factorial down to p minus k factorial by p times p minus 1 times p minus 2. And then you go down to p minus k plus 1 times p minus k factorial. The p minus k factorials cancel, and you get the formula that we're using when p is not a whole number. So in fact, if they are whole numbers, both p and k, then they're equivalent, which means that we can simply use the second formula from now on in all cases where there's a whole number or not, in order to generate those coefficients, all right, and to find the value of p choose k. Now, we do have to come up with one other thing, which is what do we have for the value of p choose 0 when p is something other than a whole number. If p is a whole number, then we can prove using the formula that you see up here, this one right here. If k is a whole number and it's 0, then we have p, it's not writing, p factorial over 0 factorial, p minus 0 factorial, which gives p factorial over p factorial, which of course is the number 1. So if it is a whole number, then we can prove that it is in fact 1. But if p is not a whole number, then we have to define it to be 1 in order to make this pattern work in all cases. So we want them to be the same formula when p is a whole number and k is a whole number, and we want them to match. So we define p choose 0 to be 1 even if p is not a whole number. All right. Okay. So now what we want to do is we want to practice just finding p choose k. So we want to practice finding p choose k on these three examples right here. You can tell that these are not going to produce finite polynomials because -3 is not a whole number, 1/2 is not a whole number, -1/2 is not a whole number. Now the choose k is going to come from the series, where the series is probably going to start at k equals 0 or n equals 0. And so we know that the denominator value is generally going to be a whole number, but the numerator value is possibly not. Maybe it is, maybe it's not. So we're going to practice now finding -3 choose 2. All right, so the 2 that you see here tells you how many factors you need in the numerator. It also tells you the factorial that you need in the denominator. So I need 2 factors here divided by 2 factorial. Now, what 2 factors? It always starts at the value of p. So the first one I'm going to need is -3. Now, what's the second one going to be? Because I've got to have 2 factors because k is 2. So this is just giving us the coefficient. This would be multiplied by x squared in the Maclaurin series or the binomial series. And so when we're looking at this, look at this pattern. Remember that the way these developed was by taking the kth derivative of 1 plus x to the p power. So you kept reducing the powers by 1 and then bringing them to the front. So you get p times p minus 1 times p minus 2 times p minus 3. So if I only have 2 of them, I start at p, and then I subtract 1 from -3 to get -4. So this has got to be -3 times -4 over 2 factorial, which is 12 over 2, which is 6. All right, so that comes out to be the coefficient 6, and 6 would be multiplied by x squared in the binomial expansion of the binomial series. Let's look at the next one, which is a different value for p. So this is 1/2 over 3. And again, let me point out that this is coming from 1 plus x to the -3 power, where the -3 corresponds to the power on the binomial, and that becomes your p value, right? So the one we're looking at now is going to correspond to 1 plus x to the 1/2 power, which of course would be the square root of 1 plus x, right? So that's the relationship, and we're trying to find a binomial expansion for this, a binomial series for it, which is really just a Maclaurin series, which is really a Taylor series, which is really a power series. So we're looking at the 1/2 choose 3, which means that I'm going to have 3 factors in the numerator of the coefficient, and I'm going to have 3 factorial in the denominator. And I start with the value of p, which is 1/2. And then I subtract 1 from it, and I get -1/2. And then I subtract 1 from that, and I get -3/2. And this is over 3 factorial. So this is going to give me a 3/8 in the numerator divided by 3 factorial. So however you want to simplify that. 3 factorial is 6. And this is going to become, if you cancel that, 1/16, I believe. Right? So, moving on now to the next one. Did I find that right? Yes, I did. Okay. Always want to double check my work. And then we can find the third one, which is -1/2 choose 4. So if I have -1/2 choose 4, then this is 1 plus x to the -1/2. The negative sends it to the denominator, and the 1/2 power is, of course, the square root. So what we're finding is a coefficient of the one on the 4th degree term, x to the 4th. We're finding that coefficient, -1/2 choose 4. So now what we have is we're going to have 4 factors on top, and it's going to be divided by 4 factorial. We start with -1/2, and then we subtract 1 each time. So -3/2, the -5 halves, the -7 halves, all divided by 4 factorial. They're all 4 negative, so 4 negatives makes it positive. This is going to give me 2 to the 4th, or 16. And then I've got 3 times 5 times 7. So however you want to simplify this, I'd probably leave it factored out. 3 times 5 times 7 over 16 times 1 over 4 times 3 times 2. 3 times 2 times 1. So what cancels? Well, the 3 cancels there, and that's about it. Nothing else goes away. So this is going to give me 35 over, I lost something. Oh, there's my 2, not 64. So 16 times 8, which is 128. Right? So we have 35 over 128. So when I'm expanding this in that term that corresponds to the 4th power, I'm going to have 35 over 128 x to the 4th. Right? Okay, let's now take a look at the next problem. So I don't know why I've got so much space here. I definitely don't need all that space. So now we want to define formally what the binomial series is. So we're making a formal definition here. For any real number p, and by real we mean real, it could be power of pi, it could be power square root of 2, which is kind of crazy, but it exists, it shows up in the real world. Then we can define the Maclaurin series for the function 1 plus x to that real number power and call this the binomial series, and it converges to the function that generated it. It generates this particular function, it converges to that for all values of x where the magnitude of x is less than 1, so between -1 and 1. And we write 1 plus x to the p is the infinite series from 0 to infinity of p choose k x to the k. And we can expand it in the way that you see right here. The first one, of course, p choose 0 is known to be 1, defined to be 1, x to the 0 is 1, so we just get 1. And then we have p choose 1, which just becomes p over 1 factorial, which is p x to the 1. And then we see the expansion for the later terms down here. Notice that the number of factors in the numerator of the coefficient matches the number of the factorial and the power on x. So all 3 of those should match. Okay. Now, what does it look like if we do a more general binomial series formula? The one that we saw up above is called the binomial series formula, and it's 1 plus x to a p power. But what if we had something other than a 1 and maybe something other than an x? We can write it as a generic a plus b raised to the nth power or the pth power. And this can also be expanded. Now, when we expand this one, we're talking in this case of n being a whole number. So when we're looking at this for a positive integer n, and again, it actually does work for whole numbers. It works for the 0th as well. It just doesn't give you anything. When you're looking at that, if you're taking a plus b to the nth, and this is a finite series, not infinite, then you choose n choose k, or you could call it p choose k, whichever one you want. And then you have a to the n minus k, b to the k. Notice that what's happening when we expand this, when we multiply this out, is that we start with a to the nth power, then we have a to the n minus 1, then we have a to the n minus 2, then a to the n minus 3, then a to the n minus 4, and so on, all the way down. And that we're doing sort of the opposite thing in the powers of b. We start with no b, which is b to the 0th power, then we have b to the 1st, then b to the 2nd, b to the 3rd, b to the 4th, and so on. So that the last one is b to the nth, and there is an a to the 0th, or no a present, because a to the 0th is 1. So we're basically going down in powers of a and going up in powers of b. And we have the coefficients given by n choose k. So when we're looking at this, we end up with this expansion that you see right here. And again, we're going down in the powers of A and up in the powers of B. Now you can use this with Pascal's triangle in order to quickly multiply out, well, quickly is relative, right? I mean, it's not super quick, but it's a whole lot quicker than doing it by hand using the distributive property. If you wanted to multiply out the binomial 2x minus 4y raised to the 5th power, notice the 5 in this case, if we're going to expand it, needs to be a counting number. So we have 2x minus 4y. We can rewrite this in that form that we had previously, which was basically a plus b raised to the nth power, all right? So if we have this a plus b to the nth power, we need this to be a plus. So we tuck the negative in as part of b. So b becomes negative 4y and a becomes 2x. And this is raised to the 5th power. So then what we do, because this is the 5th power, we're going to use the 5th row of Pascal's triangle. So when we're looking at that, let's see if we can find Pascal's triangle again. So here's the 5th row, 1, 5, 10, 10, 5, 1. All right, so that's what we're looking at, 1, 5, 10, 10, 5, 1. And coming down here, you'll see, in fact, we have the 1, the 5, the 10, the 10, the 5, the 1. So the coefficients are coming from the 5th row of Pascal's triangle, and then we go down in powers of a, starting with the nth power, where n is 5. So we should note that over here as well, n equals 5. And then what we're looking at is 2x to the 5th, and 2x to the 4th, 2x to the 3rd, 2x second, 2x to the 1st, 2x to the 0th. And then we go the opposite pattern in terms of b, negative 4y to the 0, negative 4y to the 1st, and so on, until the last one is negative 4y to the 5th. And then you multiply out each individual term, and you can come up with the binomial expansion of 2x minus 4y quantity to the 5th. Notice that in each individual term, the powers on x here, on your a and your b, add up to 5 in each term, all right? So we see that this is a 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5. And that will always happen for whatever power you're raising it to. This is much easier than multiplying it out using the distributive property and less prone to error. So if you have to do this in the future, you'll want to use this method. Okay. Now what we want to do is we just want to work some series of examples using the binomial series expansion. And we want to start with the binomial series expansion for the square root of 1 plus x. Again, the Maclaurin series centered at 0, which is the binomial series. And then we're going to use it to approximate the square root of 1.24 to 3 decimal places. And we're going to use the Maclaurin or polynomials of degree 2, 3, and 4 to see how accurate those are. And approximating the square root of 1.24. And we will, of course, assume that the series for this function actually converges to that function. Because remember, a series can converge to a different series, a different function. So a function generates it, but it can converge to a different function, which is kind of crazy, but that can happen. It converges to the actual function, remember, provided that that remainder goes to 0. And if we can prove the remainder goes to 0 for the difference between the function and the Taylor polynomial, then we can prove that the series actually converges to the function that generated it, all right, which is the case for all the ones on that common list for us. So here's what we have. This is the expansion of the binomial series here. So we have p choose k, which is defined to be p times p minus 1 times p minus 2 all the way down to p minus k plus 1 over k factorial times x to the k. So what we want to start with when we're looking at this one is we want to generate at least up through degree 4. So we need to look at these up through at least degree 4. So to do that, we need to generate at least up through the 4th one. So we need degree 4, so we're going to have to go up through at least the 4th one. So we start now by rewriting this up here. So we have f of x, which is equal to the square root of 1 plus x, which is the same thing as 1 plus x to the 1/2 power. So p is equal to 1/2. So we're going to come over here and we're going to find 1/2 choose 0, which by definition is a 1. And then we need to find 1/2 choose 1, which is going to start with p, only have one factor in the numerator, one factorial in the denominator, which is 1/2. So I'm going to box up these coefficients that we're finding. And then we want to find the next one, which is 1/2 choose 2. So now I need two factors in the numerator, 1/2, and then subtracting 1, I get -1/2. This is over 2 factorial, which is going to work out to be -1/8. All right, and then I need to go up through the fourth to get the fourth degree. So I'm going to have 1/2 choose 3, which is going to be 1/2, -1/2, -3/2 over 3 factorial. And notice that what I'm actually adding in to what I had previously is I've got the 1/2, -1/2, and a 2 factorial hidden inside here. What's new is this -3/2 in the numerator and a 3 in the denominator. So I could also take the -1/8, multiply by -3/2 and divide by 3, and that would give me the value as well. So when you work this one out, you end up basically with 3/8 times 1 over 3 times 2, which becomes 1/16. All right, so that's the next value, and we need to find one more, which is going to be 1/2 choose 4. So we have 1/2, -1/2, -3/2, and then -5/2. We have to have 4 factors in the numerator, 4 factorial in the denominator. And this is going to basically give me, well, this time I'm losing patience. So I've got -5/2, which is new, multiplied by the 1/16 times a 1 over 4, which is basically going to give me -5 over 128. All right. So again, that time I did it by what was new. So it's the previous one times the new factor in the numerator and the new number that got added to the factorial in the denominator. It already includes the 3 times 2. It just doesn't have the 4. All right. So now what we want to do is we want to expand our representation of the function. So we have f of x equal the square root of 1 plus x, which is 1 plus x to the 1/2, which becomes the series from n equals 0 to infinity of 1/2 choose n, x to the n, right? And then we can write this out. We get basically, we get the first constant, which is 1 times x to the 0 plus 1/2 x to the first minus 1/8 x squared. Where's my third one? Plus 1/16 x cubed minus 5 over 128 x to the 4th plus ... continuing in that pattern. So to approximate something, I'm just going to use the second, the third, and the fourth polynomials, and I want to approximate the square root of 1.24. So to approximate the square root of 1.24, I've got to find out what the value of x is. So now I want to approximate this value. Now, x cannot be 1.24. This only has an interval of convergence from -1 to 1. So it's got to be in there. And in fact, if we look at the pattern here, the pattern is that what's under the radical is not x, but 1 plus x. So 1.24 is equal to 1 plus x. And when I subtract 1 from both sides, I get that x is equal to 0.24, which if I rewrite 0.24 as 24 over 100, I can then reduce it to become 6 over 25. So now I want to approximate my polynomials. So I'm going to take P2 of 0.24. And P2, of course, is going to go up through the second degree. So I have a 1, plus 1/2 times 6/25 minus 1/8 times 6/25 quantity squared. All right. And if you multiply all that out and use a calculator, because it does get kind of nasty, you get 1391 over 1250. And this turns out to be exactly 1.1128. All right. Now, if I rounded it to 3 decimal places, I'd have 1.113. All right. Now I want to do the same thing for the third polynomial. The third polynomial is the same as the second polynomial plus the third term. So this is basically going to be this 1391 over 1250 plus the next term out, which is plus 1/16 times 6/25 cubed. And this one is going to give me my calculator gave up on fractions at that point, and it becomes this right here. Now, if I were to round this one to 3 decimal places, I'd have 1.114. So let's do the last one, which is P sub 4 of 0.24, which is going to be P3, which is this 1.1136664 plus the fourth term, which is a -5 over 128 times 6/25 to the 4th power. And this one turns out to be 1.1135344, which also would round to 1.114. Now, if we use our calculator to find this value, it's only going to give us an approximation, but it'll give us a good approximation, at least through the digits that it shows. This is going to be approximately 1.113552873. And we see that we've actually got the approximations matching out through the 4th decimal place. So we see that we've got some matching going on out here, and then from the 5th decimal place on, they're off. But we see that it is, in fact, quite accurate. And really, we only used 5 terms in order to get P4, with the 0th being the first term. Okay, so now what we want to do is another example. We're going to do the same thing. So what we want to do here is exactly what we did in the previous one, but this time we want to approximate using the cube root. And when we do the cube root, it's going to be the 1/3 power. So this is going to be f of x equal to 1 plus x to the 1/3 power. So in order to approximate, we're going to need to find the first coefficients. Now this says find the first 4 terms, and really I should have said find the first 4 non-zero terms. So in order to find the first 4, we need to at least find P choose 0, P choose 1, P choose 2, and P choose 3, and hope that none of them turns out to be 0, which they won't be. All right, and then we'll use those to approximate this value right here. So go ahead and work this out using the previous example as a guide, and then pause the video to do the work, and then turn the video back on, and we'll compare our answers. Okay, so we've determined that P will be 1/3. And when we expand it to the first 4 non-zero terms, we know we have to find 1/3 choose 0, 1/3 choose 1, 1/3 choose 2, and 1/3 choose 3, none of which turn out to be 0. They're not going to be because P, of course, does not start with 0. And when you subtract 1 from it, you're never going to get 0 because it's not, in fact, a whole number, so it's not possible. So when we're looking at this, we come up with 1, 1/3, -1/9, and 5/81. And then we can represent that function, the cube root of 1 plus x, using those coefficients. So you see right here, the cube root of 1 plus x is 1 plus x to the 1/3, which is the infinite series of 1/3 choose k, x to the k. And that becomes this expansion that you see here. Now, to approximate the cube root of 0.69, we have to find x. So 1 plus x is equal to 0.69. Subtract 1 from both sides. X is a -0.31. Then we'll use the first 4 terms to approximate our value, with x being negative 0.31. So we have 1 plus 1/3 of that minus 1/9 of that squared plus 5/81 times that cubed. And when you work that out on the calculator, you get this value right here. Now, again, yes, it's a lot of work by hand, but this is super easy to program into a computer or calculator to do these calculations. Whereas the algorithm for doing a cube root is much more complicated and requires more steps. And the more steps you have in an algorithm for a computer, the more you heat up the computer. And when you heat up the computer, you create errors. So you always want to try to do things in the least number of steps possible, which is one of the reasons we like using series. It gives us good approximations with fewer steps than maybe using a known algorithm that would require more steps. And so we get this approximation that you see here. And this is only using the first 4 terms of that binomial expansion. And on the calculator, we can see that we get this value right here. Notice that this one is not quite as accurate as the previous one. The cube root one was not as accurate as the square root one was. Let's now take a look at the next one. If we wanted more accuracy, we would need to take more terms, all right? So let's take a look now at this one. We want to do the same thing we've been doing. So I want you to pause the video. I want you to work out this one. Notice that we have 1 plus x to the negative 3. So p in this case is an integer, not a fraction, but we're never going to get 0 in the numerator because we'll always be subtracting. So the numbers will become more negative. So we'll never have a 0. So we're going to find the first 4 terms by finding negative 3, choose 0, which will be 1. Negative 3, choose 1, which will be negative 3. Negative 3, choose 2, and negative 3, choose 3. Then we'll use those to expand this into a power series, specifically the Maclaurin series, called a binomial series. Then we're going to use the first 4 terms to approximate 1 divided by 0.331, which of course is 1 over 1.1 quantity cubed. So we'll have to find what our x value is again. So pause the video, work this out, then turn the video back on and we'll compare our work. Okay, so when we find the first 4 non-zero coefficients, we're finding negative 3, choose 0, which is 1. Negative 3, choose 1 with 1 factor on top and 1 factorial on the bottom is negative 3. Negative 3, choose 2 with 2 factorial in the denominator and 2 factors on top, starting with p and reducing by 1 each time gives us 6. And negative 3, choose 3, starts with negative 3, has 3 factors on top, and negative 4, negative 5, over 3 factorial, which gives us negative 10. Now, when we put that into our binomial, we end up with this value that you see here. So we're trying to find a binomial expansion or binomial series for f of x equal to 1 plus x to the negative 3, which becomes the infinite series, negative 3, choose n, x to the n. And then we can use our coefficients being multiplied by x to that power in order to write the binomial expansion for it. Now we want to use this to approximate 1 divided by 1.1 cubed. So when we do that, we need to find the value of x again. 1 over 1.1 cubed, of course, is 1.1 to the negative 3, which gives it the format of our function. Then we take 1 plus x and set it equal to 1.1, subtract 1 from both sides. Remember that our interval of convergence is from negative 1 to 1, so x has to be in that range. And we get x equal to 1/10, which is definitely between negative 1 and 1. So we know it's in the interval of convergence. Then we approximating using the Maclaurin polynomial of the 3rd degree, P3, of 1/10. And when we work this out, we actually get exactly 3/4, which is 0.75. When we compute it on a calculator, it turns out that 1 divided by 1.1 cubed turns out to be 0.7513148. So you can see that it is relatively accurate. Again, we only use 4 terms. It wouldn't be too difficult to use more terms. Now, this might not be one that you would use necessarily with a binomial expansion on a computer, because it is relatively easy to multiply out 1.1 to the third power. It doesn't take any more steps than doing this right here, but it is one way to code it. It is more useful when it turns out to be an irrational number or a non-integer. Okay, we have two more examples we want to work, which is going to be starting with this one right here. Now, this one I'm going to work with you. This one is different than what we've seen before because our function does not have the correct form. It doesn't have 1 plus x raised to a power. So the first thing we're going to have to do is we're going to have to fix that. It has to have the binomial form in order to use the binomial series. So it is based on 1 plus x raised to a power. So that 2 has got to come out of there. Once we found the approximation for it and we found an expansion for it, at least for the first 4 non-zero terms, then we'll use it to approximate this value here. And again, it can be shown that the series generated by this function here actually does converge to this function. So it's another way of writing that function. So the first thing that we want to do is we want to get that 2 out of there. So the first thing is to write it in the form of 1 plus x to the p. So we're going to take this 2 plus x to the negative 2, which is our function. And we're going to rewrite this instead as 2 times 1 plus x over 2 quantity to the negative 2. So what I've done is I've factored out the 2. The first digit has to be 1. It has to be a 1 as the constant inside. So I'm going to factor the 2 off. Now I've got 2 times this quantity, both raised to the negative 2. And remember that when you have a power applied to a product, you can pull the power onto each factor individually. So this means that I can write this as 2 to the negative 2 times 1 plus x over 2 to the negative 2, which basically gives me 1 over 4 times 1 plus x over 2 to the negative 2. But now I've got something that I can actually use the binomial expansion for, because I've got the 1 here. I'll multiply it by a 1/4, and I'll replace the x with x over 2. So let's go ahead and do that as our next step. What we want to find then is the expansion for it. So we can see here that p is equal to negative 2. So we need to find negative 2, choose 0, negative 2, choose 1, negative 2, choose 2, negative 2, choose 3, in order to find the first 4 non-zero terms. So we're going to start with negative 2, choose 0, which of course is defined to be 1 whenever p is not a counting number. And so then our second one, we'll box that up so we can find it later. Negative 2, choose 1 is going to have 1 factor on top, which is negative 2, over 1 factorial, which is negative 2. So that's our second one. And then negative 2, choose 2 is going to start with negative 2, have 2 factors. So I've got a negative 3 over 2 factorial, which basically becomes 3. Double checking my work, and we need one more. 2, choose 3, which is going to, negative 2, choose 3, which is going to start with negative 2 times negative 3, one more factor times negative 4, reducing by 1 each time, over 3 factorial. So the 2's cancel, the 3's cancel, and I get a negative 4. All right, so now I want to go ahead and write out what my expansion is going to be. So I have f of x, which was equal to 2 plus x to the negative 2, which is equal to 1/4, 1 plus x over 2 to the negative 2, is going to be equal to the 1/4 of the infinite series. We'll use k equals 0 to infinity of negative 2, choose k, that's our p choose k, x to the k, except it's not x. What is it going to be? Remember, we had to substitute. So we're going to substitute x over 2 in place of x. and this is raised to the k power. Now, I can separate the 2 from the x if I want to. It's not really going to make a lot of difference. It's going to come out anyway when we do the multiplication. But you could separate it at this point if you wanted to and write it as x to the k over 2 to the k. Now, when we expand this, what we're going to end up with is we're going to get 1 as our first coefficient times x to the 0, which is just 1. And then we have -2 times x over 2 to the first, right? So we should put that in parentheses. And then we're going to have +3 times x over 2 to the second. I believe I'm keeping up with the right powers. Yes. -4 times x over 2 to the third. And then repeating in that pattern. And so the question is, do we have a pattern that's starting to develop here? And it does look like we have a pattern developing. It looks like coefficients are 1, then 2, then 3, then 4. I'm guessing the next one would be 5. So it looks like there's a pattern actually developing here, but we're just wanting to use it to approximate something. So this is good enough for us. And then we're going to use this to approximate 1 over 2.1 squared. So now let's come down here. So we want to approximate 1 over 2.1 squared, which is equal to 2.1 to the -2. So we need to find x. So that basically means that we have our format. When we're looking at our value here, we need to find the value of x, which from our original, if we want to use the original, we can use this one right here, which would be 2 plus x has to be equal to 2.1. So instead of subtracting 1, we're subtracting 2. And we find, as we found previous problem, we find that x is equal to 0.1 or 1/10. Right? And then we're going to use this P3 polynomial approximation. So P3 of 1/10 is going to be 1 minus, well, I've got 2 times x over 2, so the 2's cancel, and I just get 1/10. And then I've got +3 times 1/10 over 2 quantity squared. So the 2 squared becomes a 4, so I get +3/4 times 1/10 squared. And then I've got 2 to the third, which is 2 cubed, and 4 divided by 2 cubed is 8. So 4 divided by 8 is going to give me a -1/2. And this will be 1/10 to the third. And this is my approximation. And when I work this out, I end up with basically 907 over 4,000, which turns out to be the decimal number 0.22675. Now, on a calculator, we have this value. So I need a lot more space on this problem. So on the calculator, we're approximating 1 over 2.1 squared, which turns out to be approximately 0.226757369, and then it continues from there. And we can see that we actually on this problem have 5 places of accuracy only using the first 4 non-zero terms, so P3. So we've actually got this out to the this is thousands, 10,000s, 100,000s place, which is quite accurate. All right, so we can see that we've got a really good approximation here. And this might be simpler to code, just depends on the problem. Now, that wasn't the only thing that we were asked to find here. We did do this approximation here, but then it says that we're to assume that f converges to its actual self on the interval of convergence. But we want to know, what is that interval of convergence? Remember, when you start in this format right here, that the interval of convergence is given by the absolute value of x less than 1. But when we rewrote our problem, we ended up with this expression right here, which means that our interval of convergence is going to be when the absolute value of x over 2 is less than 1. So now when we're looking at that part, and we're looking for the interval of convergence, it is going to happen whenever the magnitude of x over 2 is less than 1, which of course, again, gives us basically that the magnitude of x is less than 2. So between -2 and 2. Now that doesn't tell us what happens at 2 or at -2. So we have to evaluate those separately. So we know it's at least between open -2 and open 2, but we're not sure about what happens at the endpoints. So we're going to check the endpoints separately. Create some space here because we're definitely going to need it. So we're going to check the endpoint as we did previously when we did the ratio test for absolute convergence. You still have to test the endpoints because it doesn't determine what happens at the endpoints. So we're going to check the endpoint x equal -2. So we're going to plug this back into our original expression for the power series, which is right here. So we're going to replace this x right here with -2. So let's see if I can copy off just this part right here. Right. And we'll see if I can paste it right here. All right. So this is our function. So f of x equals this. And when we check this, this becomes 1/4 the sum from k equals 0 to infinity of -2 choose k times -2 divided by 2 to the k. Now that's going to give me a -1 to the k. So now I need to know, do I have some pattern? Did I have a pattern developing in what I saw earlier? So I'm going to come back to what I had earlier and see if I can represent this -2 choose k in a different format, all right? Because I need to know whether or not it converges. So coming back up here, remember we said that it looked like there was a pattern developing where the coefficients were always going to be 1 greater than the index number. So the first one is k equals 0, and we have a 1 for the coefficient, then k equal 2, and we had a 2, k equal 3, and we had a, or k equal 2, we had a 3, k equal 3, we had a 4. So it was always 1 higher. So if you look up here, is that going to happen for the next value? For -2, choose 4. For -2, choose 4, you're going to add a -5 here, and you're going to have 4 factorial. And if you work it out, you're going to see that, in fact, it is actually canceling everything but that largest value. And so you are going to end up with a 5, and they're alternating in sign. So we can write this then in a format that reflects that. So what we have here basically is the series from k equals 0 to infinity. Another way of writing it without this format right here is going to be, well, it looks like it's k plus 1, and then it's going to be x over 2 to the k, and then we have a -1 to the k because it alternates sign. So this is another way of representing this series. So it's a different series. It's still a power series, but it's not based on the binomial anymore. It's not based on p choose k, but it is a different representation for the same series. So we can use this one to evaluate what we have below. So coming down to what we have below, we can represent this again, which has to be the same thing as the sum from k equals 0 to infinity of -1 to the k plus 1, and then x over 2 becomes -1 to the k. Now I've got -1 to the k times -1 to the k, which gives me, of course, 2 -1s to the k, and I can add those powers together, which is going to give me the sum, and I'm not going to write the subscripts. This is going to give me -1 to the 2k times k plus 1. And then again, I can rewrite this as -1 squared to the k, And what is negative 1 squared? Well, negative 1 squared, of course, is 1, and 1 to the k is 1. And so we basically end up with the series for k plus 1. And of course, we're going from 0 to infinity of k plus 1. Now, I know that this diverges. How do I know it diverges? It diverges by the divergence test because the limit of the sequence does not go to 0. The limit as k goes to infinity of k plus 1 goes to infinity. So it diverges by the divergence test. Now let's reevaluate at the other endpoint, which is 2. So now we're going to check the other endpoint. Again, checking one endpoint does not tell you what happens at the other endpoint. You have to check them both individually, x equal 2. So now we're looking at this value right here, and we're going to use this other format that we had right here. So we're going to have the sum from k equal 0 to infinity. So this is written without the p choose k format, negative 1 to the k times k plus 1 times x over 2 to the k. Now our x becomes a 2, so this becomes 2 over 2. And when we have 2 over 2, we get 1. So we have k equals 0 to infinity of negative 1 to the k times k plus 1 times 1 to the k, but this becomes 2 over 2 to the k, which becomes 1 to the k, and 1 to the k is 1, so it drops out. So we basically have an alternating sequence right here, but the problem is if we look at this one, we look at the even terms and the odd terms, the even terms go to infinity because they're all positive, and the odd terms go to negative infinity because they're all negative. So because we have the even terms going to one place, which is infinity, and the odd terms going to a different place, which is negative infinity, then we know, in fact, that the sequence diverges, all right? There's no value, it does not exist. The limit of it does not exist because the even terms go one place and the odd terms go another. So again, we see that it diverges, but not by the divergence test this time. All right, so what is our interval of convergence? So our interval of convergence, I, is open negative 2 to 2, all right? So you can see in this problem that we got a wider interval of convergence, and that was because we had to factor out that 2. So if you're worried about the fact that the interval of convergence is always small between negative 1 and 1, there are ways of shifting it so that it gets larger, and then we can get convergence. All right, we have one more example to work, which is taking known power series and binomial power series and finding the value of a limit. So what we want to do is we want to find a limit as x goes to 0 of 1 minus 2x to the negative 1/2 minus e to the x over 8x squared. So we're going to use the known power series for e to the x here. This 1 minus 2x, we're going to represent using the binomial series. So we're going to have to do some work on it. And then we're going to divide all that by 8x squared and see if I can take the limit and come up with what the value of the limit is. So the first thing I need to do is I need to write down what the representation for 1 minus 2x to the negative 1/2 is. So if I'm looking at the function here, where f of x is equal to 1 minus 2x to the negative 1/2, then I can rewrite this as 1 plus a negative 2x to the negative 1/2. And this would be where p is a negative 1/2, and I replace x with negative 2x in the binomial expansion, in the binomial series. So this is going to become, if I put it into this format right here, the series from k equals 0 to infinity of negative 1/2 choose k times replace x with negative 2x raised to the k power, right? So if I want to use this to evaluate a limit, I'm going to have to write out at least some terms. So let's go ahead and write out maybe the first 3 or so terms on this thing, all right? So let's go and write out the first 3 or 4 non-zero terms. So we're going to find -1/2 choose 0, which of course we know turns out to be 1. And then we're going to have -1/2 choose 1. And I believe that we have already done this somewhere else in this particular set. So let's see if we can find it. No, that's +1/2. That won't be the same. That's 1/3. Thought I found it. Maybe I didn't. Okay, I guess not. I would have sworn we did this before, but maybe I'm just remembering doing it myself. So this turns out to be -1/2 over 1 factorial, which is -1/2. And then we're going to have the next one, -1/2 choose 2, which is -1/2 times -3/2. I think maybe when we were practicing finding P choose K, we did one of these. And this is going to turn out to be 3/8. Box that up. And then let's do maybe one more. -1/2 choose 3, which is going to turn out to be -1/2 times -3/2 times -5/2, subtracting 2/2 each time over 3 factorial. Working that out becomes -5 over 16. All right. So now we have those terms. So I'm going to put these into my limit. And I'm taking the limit as x goes to 0. So I have the limit, and I'm going to have to write relatively small to get all this in there. 1 minus 1/2 x to the first. Oh, wait, it wasn't x, it was 2x, -2x. Okay, so I need to replace this with a -2x to the first. And then my next term is going to be plus 3/8 times -2x squared minus 5/16 times -2x cubed plus ... All right, so it keeps going. Now, the other part that I have in my thing is e to the x. So I want to write this exponential in terms of its Maclaurin series, which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So I'm going to then subtract, so let me put this in a different color, minus 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... right? And then all of this is divided by, in the limit, 8x squared. Okay, now I need to go ahead and work out what these terms come out to be. So you can take some time and work those out. And I'll just give you the value of it right here. So I have the limit as x goes to 0. And now I'm going to write this becomes 1 plus x plus 3/2 x squared plus 5/2 x cubed plus ... And then the next one for e to the x minus 1 plus x squared over 2 plus x cubed over 6 plus ... divided by 8x squared. Now I'm subtracting the second expression from the first expression, and they both have a 1 plus x. So the 1 plus x's are going to cancel. And then I've got 3/2 x squared minus x squared over 2. So the next thing that I'm going to get when I combine those is I'm going to get 3/2 minus 1/2 times x squared. So 3/2 minus 1/2 attached to the x squared plus, and then I'm going to have 5/2 minus 1/6 attached to the x cubed plus ... attached to x to the 4th, and so on. And all of this is now divided by 8x squared. Now, I know that 3/2 minus 1/2 is going to give me 1. So I have the limit as x goes to 0 of x squared, and 5/2 minus 1/6 turns out to be 7/3 x cubed plus ... All of these have higher powers of x to the 4th, x to the 5th, and so on. And I'm dividing by 8x squared. If I divide each of the terms in the numerator by x squared and the 8, then I'm going to end up with the following. I'm going to get the limit as x goes to 0 of x squared over 8x squared minus 7/3 x cubed over 8x squared plus ... And this becomes the limit as x goes to 0 of 1/8 minus, what was that, 7 over 24x plus ... And it keeps going on from there. All right. I think that's a plus. Yeah, that should be a plus. I don't know where that became a minus, but that should be a plus. Now, each of these terms back here is going to have a higher power of x. The next one's going to be x squared, then x cubed, and so on. So when I take the limit as x goes to 0, the second and later terms are all going to zero out, and I'm left with the limit of 1/8, right? And so that gives me my limit value. Right? So hopefully this makes sense to you, that you understand now how you can use a known power series to find other power series, how you can evaluate limits with them, how we can find a binomial expansion for a binomial raised to any power that's real. And I hope that you have enjoyed this section on series. In the next set of videos, we'll be taking a look at parametric and polar equations. I hope to see you there.